list questions. This is still coming out of that 5.2 packet of the acid-base reactions, buffers and titrations from South Pasadena. So her third question had to do with problem number 5 on here. And I guess when looking at the key, it appears that the reaction is flipped over from what's described. So in the problem, it says if exactly 50 milliliters of 0.050 molar hydrochloric acid, and anytime you're looking at these, you really got to take note of if you got strong or weak situation. So like just kind of make a mental note that this is a strong acid. So that is added to exactly 50 milliliters of the same concentration, 0.050 molar of ammonia, which is that NH3 stuff. And we've talked about how that's a weak base. Most of our bases that we see follow the Bronsted-Lowry definition, which would essentially mean it would have a hydroxide on it. But for AP purposes, this is probably one of the only ones you're going to see that does not have a hydroxide, and you just need to know that ammonia is a base. So the first thing that I notice is that since I have the same volumes and the same molarities being mixed together in this titration, so like this is what's going on over here. So we mix them together, right? Since these volumes and these molarities are the same, this is where moles of acid are going to equal moles of base. And by definition, that is the equivalence point. And so there's something interesting that happens, just like kind of going off of that last question I worked out in that first video. The purpose of the two Rice charts was so that you could tell that when you mix these two things together, this is where the moles of acid equals the moles of base. And so like what it's describing is that we're mixing HCl with NH3, right? But since it's moles of acid equal moles of base, these two things have completely neutralized each other. Well, since NH3 is a weak base, that means it has the ability, when you mix it with a strong acid, to produce its conjugate. And so the definition of a buffer is if you have a weak base and its conjugate, which its conjugate will be produced when this stuff starts doing its mixing over here. This is what we get with this weak base picks up this hydrogen because HCl is strong. It wants to dissociate into H plus and Cl minus. And so that H plus goes and sticks on the NH3, making NH4 plus, leaving Cl minus behind. And so if I have both this and this present in the same environment, then that's the definition of a buffer. And so since both of these, the strong acid hydrochloric acid and the weak base ammonia, have neutralized each other under these conditions, there's none of this left. But since I have this present, because if these two things have reacted away, that means they've produced this stuff over here. If I have ammonium, NH4 plus present, then it can be doing something in that mixture. It can still be working on the water that's present in there because there's always water in these solutions. So that's why it seems like we flip this reaction, because this is at the equivalence point. And so these two things are gone, leaving this is the only thing present. And so if that's the only thing that's in there, well, it's in there with some water. And what is it doing? It's a weak acid. And so if it's a weak acid, it can donate its proton back to that water to make NH3 and H3O plus, which we normally just write as H plus, but that's fine. They mean the same thing. And so now we can, if we're trying to calculate the pH, of what's happening at this exact moment in time, we have to think about what is this NH4 plus doing with the water, because these two things are gone. They've neutralized each other because they're at the equivalence point. So we got to think about what the NH4 plus is doing. So I didn't show the original Rice chart to kind of calculate this, but it's easy enough because we know that, what do we know? We want to know how many moles of NH4 plus are in there. So the number of moles of this that are present is going to be equal to the number of moles of these things, because these things neutralized each other. And when they neutralized each other away, they produced NH4 plus. So to find that, we just say, well, we had 50 milliliters and we multiply it by its molarity. And that comes out to be 2.5 millimoles. So I had 2.5 millimoles of HCl, 2.5 millimoles of NH3. I mixed them together. They neutralized each other, so these two things go to zero. Well, when they do that, going to zero, that means I've now got 2.5 millimoles of NH4 plus present. So now I'm down here ready to do my Rice chart, but we're going to convert everything back to molarity because that just simplifies the process for when we get to our K values. And so if I have 2.5 millimoles of NH4 plus, the volume that's in now is just the volume of these two things because we've added this together. So the total volume of the solution is 100 milliliters. So 2.5 millimoles over 100 milliliters will tell me that this is 0.025 molar. So I have 0.025 molar NH4 plus. We don't ever care about the water because it doesn't affect how the equilibrium lies. And these things are zero because they've neutralized each other away. But this NH4 plus is still weak, and so it can still donate a proton to make more of this. It just doesn't do it very well. Excuse me. So we do our regular Rice chart. Plus x, x, x. And then in this particular question, in the text of the question, it did not give you the K value. You would need to know that, and it's assumed that you knew to go retrieve that from an appendix or to look that up. Now, you're not going to find a Ka for this, but you can get a Kb for that. Like if you look up on a chart, you're going to be able to find a Kb for that in the appendix. If this question was on an AP exam, they would have given you this Kb. They would have told you the Kb of ammonia, and it might very well be in another question. I don't remember if you had to use ammonia on a different question and it was provided to you. But if I look that up, I find that the Kb for ammonia is 1.8 times 10 to the negative 5. And I don't want the Kb, I want the Ka for this ammonium because I'm producing H3O plus. And so when I solve for X, I'm going to be solving for my H plus value. So I need this to be Ka. So again, Ka times Kb equals Kw, which is 1 times 10 to the negative 14. So just some basic algebra. 1 times 10 negative 14 over 1.8 times 10 to the negative 5. And I calculated that the Ka here was, 5 point, I didn't actually write it down. I think it's like 5.55 times 10 or times 10 to the negative 10, but I'm not absolutely here. Let me calculate it. Let's see. Negative 14 divided by 1.8, negative 5. Yeah, 5.56 times 10 to the negative 10. Okay, so we got that, and now we can just set up our regular old Ka equals, in this case, it's NH3, H3O plus, or H plus, whichever you prefer, over the NH4. And then whatever's happening at equilibrium are the values that we're going to substitute in there. So this really just becomes x squared over 0.025. So x squared over 0.025, because we're going to call this x negligible. It's a really, really small value. If you go on to college chem, you'll learn the 5% rule. We've talked about that, where you go ahead and assume it's negligible, and then you have to double check. And then if it's not negligible, you go back and you solve with a quadratic equation. That's kind of the easiest way to approach that. So anyways, when you solve for x here, I got that x equaled 3.73 times 10 to the negative 6. And then, of course, that's equal to the hydrogen concentration. And you take your negative log of that to get your pH is 5.43. I think the answer key that I posted online, it was just a little bit off because they used a KB value that maybe was carried out to a couple more extra decimal places or something. But it should be right around there, right around 5.43. And then again, sig figs discussion, since pH is a log value, the number of decimal places needs to match the smallest number of sig figs from our original problem, which I guess technically was 1 because there's not a decimal here. I don't love that. I think the question should have been written with a decimal there so that we would have had 2 sig figs, and then this would be appropriate. Okay. The next question that came from Miss Kayla was pertaining to the first free response, the one from 2002B, number 8, the one that had the graph that went along with it. And her question was about part B. So this is from the free response 2002B, number 8, and it was part B to that question. So it says, describe one method by which the value of the acid dissociation constant for HA can be determined using the graph above, which essentially is asking, how can you use the graph to find Ka? And so what we have to know, and I'm going to show you this picture that I've scribbled on a bit. What you have to notice, or I guess paid attention to in the context clues. First off, they're talking about this being a weak acid. So we know it's a weak acid. And if it's a weak acid, it's got a buffering section that happens. Another way we can tell it's a weak acid is the fact that it's got that little kind of blip, that lip thing going on there. So that tells you it's a weak acid. Excuse me. And so if it's a weak acid, there's a relationship that happens at this thing called the half equivalence point. So again, the equivalence point occurs, you find kind of the most vertical region of the graph, and wherever that kind of midpoint is, that's what we would call the equivalence point. So this is the equivalence point here. If I drop that down, I find that the equivalence point happens after I add 25 milliliters of this base. Well, halfway to that volume is 12.5 milliliters. And so that halfway point is called the half equivalence point. Well, the half equivalence point, and I mentioned this in the last video, is where just from your weak component, not from the addition of whatever's in the burette. So if we have something that's weak down here, weak acid or a weak base, whatever, it has the ability to have HA and A minus present after we kind of start dripping some of our stuff from our burette down in there. Once that happens, then you have a buffer. And if you have a buffer, according to Henderson-Hasselbalch, pH equals pKa plus the log of A minus over HA. Remember that formula is on your formula chart, so you don't have to memorize that, although we use it quite a bit. You probably won't forget it. If A minus and HA are equal to each other, then this whole term becomes a 1, making this whole term a 0. And if this whole term is 0, then pH equals pKa. Well, by definition, at the half equivalence point, excuse me, that is where HA is equal to A minus. So what we know is, since it's at that half equivalence point, you can use the graph to kind of identify that. You just say, oh, I know this is a titration curve for a weak acid, because 1, they tell me, but 2, I kind of recognize that this lip lets me know that I have something weak being titrated here. Find that equivalence point and then backtrack to where half of that volume is. That's called the half equivalence point. Sorry. So if we're at the half equivalence point, we know pH equals pKa. Well, we can find the pH just by interpreting the graph. So the pH is happening here at 5, looks like to me, at that half equivalence point. So if the pH is 5, that also means the pKa is 5. And, and then Ka, remember, putting a P on something just means to take the negative log of it. So to kind of go in the reverse direction, we would do 10 to the negative 5, which would make this 1 times 10 to the negative 5 for the Ka. So that's how you can use the graph to determine what the Ka is, if it's weak, because this whole jazz, like, you have to have something weak present for us to, have this buffer situation going on. So this is true if you have a weak acid or a weak base being titrated with something that's strong. At the halfway point to the equivalence point, pH equals pKa. And if you can interpret, and that's not even a word, interpret your graph to find your pH, then you can in turn take your pKa to solve for your Ka. Man, I'm sorry. Okay. The last question that Kayla sent over to me came from that same free response, but it was from part C. And it says, on the graph, sketch the titration curve that would result if 25 milliliters of 0.1 molar HCl were used instead of 0.1 molar HA. So essentially, they're asking us to identify how is it different if the acid is strong. So the graph that they provide was for a weak acid, but now they're saying, well, what if we replace that with a strong acid? So let me sketch a little picture. We got our burette. They didn't tell us that we're changing anything up here. I think this was kind of in the stem of the question. They tell us it's 0.1 molar NaOH. So we have strong base up there. And then down here, instead of weak acid, we're going to put 0.1 molar HCl. So that's strong. And it did tell us that this was 25 milliliters. Okay, so a couple things. When you're trying to sketch a graph, there are a few key points that you need. Like if they ask you to take this data and sketch a graph from it, they don't give you anything else. There's a few key points that you got to have. So on this axis, we're going to have pH. Over here, we're going to have volume. And in this case, this is the base. So what this is representing is how much stuff was added from the burette. So how much stuff did we have to add from the burette? So the first point that we can graph just by doing some simple math is, what is the pH before we add anything from the burette? Like, what is the pH where this volume is 0? And so all that really means is, what is the pH of the stuff that's in here? So that's 0.1. So that's somewhere over here. That's 0.1. The second point that when you're sketching that you really need to know is what is the pH at equivalence? What is the pH at equivalence? And so that's going to be somewhere in here. This is kind of arbitrary. So pH at the equivalence point. And remember, that's where moles of acid equals moles of base. If you have those 2 points, you can plot them on the graph and then sketch just kind of a generic curve, and you're pretty good. The ones we did in class, I tried to kind of push you guys to work through some questions. I had you kind of plot a point in between this initial point and equivalence point, so somewhere like in this area. And then I had us plot 1 point after equivalence, so somewhere over here, so we could get more of that S curve. But if you know just the basic fundamentals of the titration curves, and I left you guys a video. It was a little handout that had a bunch of titrations on it, and then up at the top there was a link, and you could just type in the URL for a Vimeo video, and I think it requires a password. I hand wrote the password on there. But she kind of goes over and reviews all the fundamentals of generic titration curves. But anyways, if you can sketch those 2 points and you know like what a basic titration curve looks like, then that's all you need if you can calculate those 2 things. So this first point, all we need to know is what's the pH of this stuff in here. Well, remember, if the stuff in here is strong, that is super easy to calculate, the pH, because HCl is strong, which means it completely goes to H plus and Cl minus. There is no HCl left. And the reason that's important is if I have 0.1 molar of this, then when it completely dissociates, it's going to produce 0.1 molar of H plus and 0.1 molar of Cl minus. And if I know H plus, then I can calculate pH. So pH equals negative log of 0.1, which is just 1. So what that means is before we add any base, the pH of this strong acid is 1. So I'm just going to kind of like sketch a 1 on here. There's 1. So that's my starting point. My second point would be at equivalence. So that's where moles of acid equal moles of base. They tell us, and I guess recall, MAVA is the same thing as saying moles of acid, and MBVB is the same as saying moles of base. So they tell us that the molarity of the acid is 0.1. The volume of the acid that we started with down there was 25. I'm going to set that equal to, they told us the molarity of the base to be 0.1. And we want to know what is the volume of the base, because we're trying to figure out where that point lies down here. And hopefully you can recognize that that's pretty simple, like things cancel out. So the volume of the base happens at 25 milliliters. So I need to drop a point at 25 milliliters. That's where my pH is going to be on my x-axis. But then what about on my y-axis? Like, how do I know how far it is? What do I label this or whatever? Well, if this is a strong base and this is a strong acid, as long as they are equimolar, let me write that down in case you can't hear me. I don't know if I'm spelling that right. Probably not. Equimolar, which means of the same molarities. If they are equimolar, which they are, 0.1 molar, 0.1 molar, then when they neutralize each other, since it's strong and strong, the pH is neutral, or it has an equivalence at pH of 7. pH 7. So I plop that point in. 25 milliliters, the pH hits 7. And the generic curve for a strong titration, it does not have that little weird lip that happens here. It's just flat until it approaches that volume where, or it's essentially flat, pretty close to flat, until it hits that volume where it shoots straight up to the equivalence point, and then it goes up and eventually levels off, usually somewhere around 13. Somewhere around 13 pH. And so that is what they're asking you to kind of sketch on there. And I did a bad job of it here. But starts down here where the pH is 1. It kind of goes. The equivalence point still happens at 25 milliliters, but it occurs at pH of 7. And so I just shoot that on up, and it levels off somewhere up there around 13. So that's what they were asking. And I mean, I did a lot of extra work here just kind of to help you understand, but essentially all you had to know was that since it's strong acid, strong base, and they have the same molarities, the equivalence point's got to happen at 7. I didn't really have to calculate anything to be able to tell me that. And then this, since it was a strong acid, pH equals negative log of 0.1. So I have to start at 1. And I didn't pull the rubric for this, but I would imagine on that particular question, they were looking that you started this at 1 and you put the equivalence point at a pH of 7. That would be my guess. Okay, so if you guys have any more questions, just shoot them over to me by email. I'll be reaching out pretty soon with information of kind of how we're moving forward, and I hope you guys have a good night.